Hello again. This is Math 2245 coming to you from the College of DuPage, and the title of this lecture is Numerical Considerations, Partial Pivoting, and Ill-Conditioned Systems, offered on Juneteenth 2023. As always, please be attentive while watching this video. By way of introduction, now that you understand the basic Gaussian elimination technique, it's time to turn it into a practical algorithm that can be used for realistic applications. For pencil and paper computations where you're doing exact arithmetic, the strategy is to keep things as simple as possible, like avoiding messy fractions, in order to minimize stupid arithmetic errors that we're all prone to make. But very few problems in the real world are of the textbook variety, and practical applications involving linear systems usually demand the use of a computer. Computers don't care about messy fractions, and they don't introduce errors of the stupid variety, but they produce a more predictable kind of error called round-off error, and that's important to spend a little time up front to understand this kind of error and its effect on solving practical, large linear systems. Numerical computation, as we've discussed in digital computers, is performed by approximating the infinite set of real numbers with a finite set of numbers, as described below. These are called floating point numbers. So a t-digit base beta floating point number has a form f is equal to plus or minus, and you have decimal expansion t decimal places, times beta to the epsilon, and the first digit doesn't equal to 0 for it really to give you the right number of digits, and the base beta, the exponent's epsilon, and the digits are integers. So for internal machine representation, beta is 2. Its binary representation is standard. But for pencil and paper examples, it's more convenient to use beta equal 10, base 10. And the value of t is called the precision. And the exponent epsilon can vary with the choice of hardware and software. Now, floating point numbers are just adaptations of the familiar concept of scientific notation with beta equal 10. And those will be the values that we use in our example. For any fixed set of values, the corresponding set of floating point numbers is necessarily a finite set, so the real numbers can't be found in that set of numbers. There is more than one way of approximating real numbers with floating points, and so we have to have a rounding off convention, and that's what we're going to do. And so floating point of x, that's FL floating, is defined to be the nearest element in the floating point arithmetic to x, and in the case of a tie, we round away from 0. And so that means we define that the floating value of x, if the t plus 1 digit in x is there, and we make sure that d1 doesn't equal 0, we round down if we're less than 5, and if we're bigger than or equal to 5, we round up. And so in 2-digit base 10 floating point arithmetic, the floating value we get for 3 out of 80, which is the floating value of this, is 0.38, or 0.38 times 10 to the minus 1. And also, if you consider this example for eta and this for c, with base 2, with 2-digit rather, base 10 arithmetic, it's easy to see that when you add, your round-off error accumulates, and also when you multiply, and so you cannot assume that these things are equal. This means that caution is advised. Moreover, several familiar rules of arithmetic don't hold for floating point arithmetic, and associativity is one example. So that makes the analysis of floating point computations difficult, and there are courses in this called numerical analysis. It also means that you must be careful when working examples and exercises in some text, because most calculators and computers can be instructed to display varying numbers of digits, but most of them have an internal precision which calculations are performed before the numbers are displayed. And this internal precision cannot be altered. And so the internal precision of your calculator is greater than precision called for by the examples and exercises in this book. So each time you make a t-digit calculation with a calculator, you should manually round it to t-significant digits and then re-enter. In other words, don't chain operations on your calculator or computer in understanding these examples. Okay, so let's understand how to execute Gaussian elimination using floating point arithmetic. And let's look at this, this problem. So here's a system of two equations and two unknowns. Now, if we do this with pencil and paper in exact arithmetic, we multiply the first equation by the multiplier 89 over 47, subtract the results, and we get this as the triangular form. And back substitution tells us the exact solution is x is 1 and y is minus 1. But if we use three-digit arithmetic, the multiplier, the floating value for m, the multiplier 87 over 47 ends up being 1.89. And these other calculations end up being this. So if we do the first step of a three-digit Gaussian elimination, what we'll get, and we'll have we'll have floating point values here, and so we'll get 47, 28, 19, 0.2, 0.1, and 0.1. But that means that we don't have a 0 here, so we can't do back substitution. And since the goal was to triangularize the system to produce a 0 in that position, this can't be accomplished with three-digit arithmetic unless we make the circled value, this 0.2, 0, and then back substitution can happen. And that's in fact what happens. We will enter 0 on this to annihilate the value of the floating point number that might actually appear. And so what will happen is that instead of having 0.2, we will have 0. And then if we apply three-digit back substitution, we will get that y is 1, which it was before, but x now is a different number. X is minus 1.91. Whoa. The vast discrepancy between the exact solution and this solution, actually both of those were wrong, I'm sorry, illustrates some of the problems that we can expect to encounter when trying to solve linear systems with floating point arithmetic. Sometimes using a higher precision may help, but this isn't always possible because all machines have natural limits that make extended precision arithmetic impractical past a certain point. And even if it's possible to increase the precision, it may not buy you much because there are many cases for which an increase in precision does not produce a comparable decrease in the accumulated round-off error. Given any particular system or any particular precision, say t, it's not difficult to provide examples for which the computed t-digit solution is just as bad as the one in our three-digit example above. Although the effects of rounding can almost never be eliminated, there are some simple techniques that can help minimize these machine-induced errors, and these are used in many software programs. And the first one they're going to talk about is partial pivoting. At each step, what we do is search the positions on or below the pivot positions for the coefficients of maximum magnitude. Here, maximum magnitude means absolute value. If necessary, perform the appropriate row interchange to bring this maximum coefficient to the pivot position. This is illustrated below, where these are the values you're looking at, or the S. And so we search the positions in the third column marked S for the coefficient of maximal magnitude, and if necessary, interchange rows to bring this into the circled pivot position. Simply stated, the strategy is to maximize the magnitude of the pivot at each step by using only row exchanges. Now on the surface, it's probably not apparent why partial pivoting should make a difference, but this next example will show why it does indeed make a great deal of difference and what makes the strategy effective. So here's our example. So we're looking at this problem. This is minus 10 to the minus 4x plus y equal 1, and x plus y is 2. Now the exact solution to this problem is given by x equal 1 over 1.0001, and y is equal to 1.002 over 1.0001. both of these numbers are very close to 1. Y is just a little bit bigger than 1, and X is just a little bit less than 1. If three-digit arithmetic without partial pivoting is used, then the result, and you can see it here using row elimination, what we will get is that X is equal to 0 and Y is equal to 1. And this is because this number is what it is, and it's going to swamp the other one. So although the computed solution for Y is close to the exact solution for Y, in this case the computed solution for X is not very close at all to the exact solution for X. And the computed solution for X is certainly not accurate to 3 significant digits as you might hope. Now, if three-digit arithmetic with partial pivoting is used, what you do is you switch these 2 rows and you're pivoting there. So this is the calculation that you do. And when you do the calculation with three-digit arithmetic, now you get X is 1 and Y is 1, which is as close to the exact solution as you might reasonably expect. The computed solution agrees with the exact solution to 3 significant digits. Now, why did this make a difference? Well, without partial pivoting, the multiplier would be 10 to the 4th, and this is so large it completely swamps the arithmetic involved in the relatively smaller numbers 1 and 2 and prevents them from being taken into account. That is, the smaller numbers 1 and 2 are blown away as though they were never present, and our computer model produces the exact solution to a different system, namely this one. With partial pivoting, the multiplier is 10 to the minus 4, and this is small enough so that it does not swamp the numbers 1 and 2. In this case, the three-digit computer produces the exact solution of this system, which is close to the original system. In summary, the villain was the large multiplier that prevents some smaller numbers from being fully accounted for, thus resulting in the exact solution of another system, a different system from the original system. By maximizing the magnitude of the pivot at each step, we are minimizing the magnitude of the associated multiplier, and that helps to control the growth of numbers that emerge during the elimination process. This in turn helps circumvent some of the effects of round-off error. And we can discuss this more later, perhaps. We'll see how the term goes. But when partial pivoting is used, no multiplier ever exceeds 1 in magnitude. To see this as a case, consider the following 2 typical steps. And you got P, Q, and R. The pivot is P, and Q over P and R over P are the multipliers. If partial pivoting has been employed, then you have these absolute value relations, and so in each case, the multiplier or the resulting number after you multiply, these multipliers are less than 1. So by guaranteeing that no multiplier exceeds 1 in magnitude, the possibility of producing relatively large numbers that can swamp the significance of smaller numbers is much reduced. Not completely eliminated, however. And to see that there's more to be done, let's consider the following example. So consider this equation, and what you can see here is that this number is okay, but there's a big scale difference between the numbers that are here. Okay. So, and we've talked about this solution before, it's given here by, and suppose we did three-digit arithmetic with partial pivoting is used, and when we do that, back substitution gives us x equal to 0, not just 1, and y is this instead of 1. And this is actually bad because the computed value for x is terrible. So what's the source of the difficulty here? Well, this time the multiplier cannot be blamed, but the trouble stems from the fact that the first equation contains coefficients that are much larger than the coefficients in the second equation. That is, there's a problem with scale due to the fact that the coefficients are of different orders of magnitude. Therefore, we should somehow rescale the system before attempting to solve it. So, if the first equation example above is rescaled, multiply all the way through by something, so that the coefficient of maximum value is 1, and we could multiply all the way through by this, then the system, a different system is obtained, and we know that the example that partial pivoting there then produces very good approximation of the solution. This points to the fact that the success of partial pivoting can hinge on maintaining the proper scale among the coefficients. Therefore, the second refinement needed to make Gaussian elimination practical is reasonable scaling strategy. Unfortunately, there's no known scaling procedure that will produce optimal results for every possible system, so we must settle for a strategy that will work most of the time. This strategy is to combine row scaling with column scaling, multiplying selected columns of the matrix by non-zero multipliers. Now, recall that row scaling does not change the exact solution, but column scaling does. And so column scaling is equivalent to changing the units of the kth unknown. For example, if the units of the kth unknown, x sub k, are millimeters and the k column is multiplied by 0.01, then the kth unknown in the scale system is 1,000 exabyte, and the units of the scaled unknown become meters. Now, experience has shown that the following strategy for combining row scaling with column scaling works reasonably well. Choose units that are natural to the problem and do not distort the relationship between the sizes of things. These natural units are usually self-evident, and further column scaling past this point are not ordinarily attempted. And row scale the system so that the coefficients of maximum magnitude in each row is equal to 1. That is, divide each equation by the coefficient of maximum magnitude. So, partial pivoting together with scaling strategy that we just described makes Gaussian elimination with back substitution an extremely effective tool. Over the course of time, this technique has proven to be reliable for solving a majority of linear systems encountered in practical work. Now, although it's not extensively used, there is an extension of partial pivoting known as complete pivoting, which in some cases can be more effective than partial pivoting in helping to control the effects of a round-off error. Complete pivoting, what you do is you have the augmented matrix at the kth step of Gaussian elimination. Search the pivot positions together for every position in A. That is below it and to the right. So we're looking across not only the column, but we're the column we're in. We look across all the rows as well. If necessary, we perform appropriate row and column interchanges. Now, the row interchanges don't cause a problem, but the column interchanges do cause us to change the labeling of the variable, so we have to be careful with that. So shown below is the third step in a typical solution. You look at all these, search all the positions marked S for the coefficient of maximal magnitude, and if necessary, interchange rows and columns. And recall that the effect of a column interchange is equivalent to permuting or renaming the associated unknown. Now, you should be able to see that complete pivoting is at least as effective as partial pivoting. Moreover, it is possible to construct specialized examples where complete pivoting is superior to partial pivoting, and there's some famous examples. However, one rarely encounters systems of this in nature, and so we may talk about this, time permitting, later. Let's look at another example then. So here, use 3-digit arithmetic with complete pivoting to solve this problem. Since 10 is the coefficient of maximum magnitude that lies in the search pattern, interchange the first and the second rows, and then interchange the first and second columns. So we do that here. The effect of the column interchange is to rename the unknowns to x hat and y hat, where x hat is y and y hat is x. Back substitution then tells us that we get y hat is -8 and x hat is -6. And so that means that x is -8 and y is -6. And in this case, it agrees with the exact solution. If only partial pivoting is used, the 3-digit solution will not be as accurate. However, if scaled partial pivoting is used, the result is the same as using complete partial pivoting. So, if the cost of using complete partial pivoting was nearly the same as the cost of using partial pivoting, we'd always use complete pivoting. However, it's not difficult to show, a serious student might want to do this, that complete pivoting nearly doubles the cost over straight Gaussian elimination, and partial pivoting adds only a negligible amount. Couple this with the fact that it is extremely rare to encounter a practical system where scaled partial pivoting is not adequate and complete pivoting is, it's easy to understand why complete pivoting is seldom used in practice. Gaussian elimination with scaled partial pivoting is the preferred method for dense systems. And dense systems mean there's not a lot of zeros of moderate size. Here's your low stakes assessment, or one of the two in this. Consider the following system, and the coefficient matrix here is a famous matrix named after Hilbert. It's called the Hilbert matrix. So here's what you're supposed to do. First, convert the coefficients to 3-digit floating point numbers, and then use 3-digit arithmetic with partial pivoting, but with no scaling, to compute the solution. For part B, again use 3-digit arithmetic, but row scale the coefficients after converting them to floating point numbers, and then use partial pivoting to compute the solution. Number C, proceed as in part B, but this time row scale the coefficients before each elimination step. And lastly, now use exact arithmetic on the original system to determine the exact solution and compare your results here and discuss. We now turn our attention to what are called ill-conditioned systems, and these are even nastier. Gaussian elimination with partial pivoting on a properly scaled system is the most fundamental algorithm in practical use in linear algebra. However, it is not a universal algorithm, nor can it be used blindly. The purpose of this section is to make the point that when solving a linear system, some discretion must always be exercised, because there are some systems that are so inordinately sensitive to small perturbations that no numerical technique can be used with confidence. Let's look at an example. So consider this system for which an exact solution is x equal 1 and y equal -1. Now, if B2, which is this one, which is 0.67, is only slightly perturbed to become, instead of a 0.067, to become 0.066, the exact solution changes dramatically to become x hat equal -666 and y hat equals 834 instead of the exact solution. So this is an example of a system whose solution is extremely sensitive to a small perturbation. This sensitivity is intrinsic to the system itself and is not the result of any numerical procedure. Therefore, you cannot expect some numerical trick to remove the sensitivity. If the exact solution is sensitive to small perturbations, then any computed system cannot be less so, regardless of the algorithm made. So you're going to have something that's called an ill-conditioned system. In fact, here's the definition. An ill-conditioned linear system is said to be ill-conditioned when some small perturbation of the system can produce relatively large changes in the exact solution. Otherwise, the system is said to be well-conditioned. It is easy to visualize what causes a 2-by-2 system to be ill-conditioned. Geometrically, two equations and two unknowns represent straight lines, and the point of intersection is the solution for the system. An ill-conditioned system represents two straight lines that are almost parallel. And here you can see what's happening there. So if you slightly change something, you can dramatically change where the point of intersection happens. Now, in dealing with an ill-conditioned system, the engineer or scientist is often confronted with a much more basic and sometimes more disturbing problem, and that of simply trying to solve the system. Even if a minor miracle could be performed so that the exact solution could be extracted, the science or engineer might have still have a nonsense solution that could lead to a totally incorrect conclusion. This problem stems from the fact that the coefficients are often empirically obtained by measurements and are therefore known only within certain tolerances. For an ill-conditioned system, a small uncertainty in any of the coefficients can mean an extremely large uncertainty may exist in the solution. This large uncertainty can render the exact solution totally useless to the system that you have because your data is wrong. Your coefficients were wrong. Let's look at an example. So suppose you have this system and the numbers B1 and B2 are the results of an experiment and must be read from some test instrumentation. And the dial, the test instrumentation, can only be read to a tolerance of plus or minus 0.001. So that means that the values that were read were 0.168 and 0.067. Respectively. Well, we've already looked at this one. We knew that the exact solution of the system was this, but the small uncertainties that we have at the dial could have us having solutions looking like this or like this, dramatically different. You see, we don't know. Would you be willing to be the first to fly in a plane or drive across the bridge whose design incorporated a solution to this problem? Well, I wouldn't. There's too much uncertainty. Since no one of those solutions can be preferred over any others, it's conceivable that totally different designs might be implemented depending on how the technician reads the last significant digit on the dial. Due to the ill-conditioned nature of an associated linear system, the successful design of a planar bridge may depend on blind luck rather than on scientific principles. Now, rather than trying to extract accurate solutions from ill-conditioned systems, engineers and scientists are usually better off investing their time and resources trying to redesign the experiments or their data collection methods and avoid ill-conditioned systems. There's one other discomforting aspect of an ill-conditioned system. It concerns what students refer to as checking the answer by substituting a computed system back into the left-hand side of the original equation to see how close it comes to satisfy the system. That is, producing a right-hand side. More formally, if xc, this is your solution, is xc1, xc2, all the way to xcn, is the computed system for this values for x that we have. That's the vector where this is the system that we think we have. Then these numbers, where you take the difference between your value and the right-hand side, are called residuals. And suppose you compute an x sub c and substitute back in, the residuals are all small. Does this guarantee that x sub c is close to the exact solution? And surprisingly, and I won't prove that here, but the answer is no when the system is ill-conditioned. Ouch. And let's go back to the one of the ones we talked about before. And this was the example we talked about, I think the very first one in this section. So you compute the solution to be this, and you try to check this error. If you substitute it in, you'll get the residuals are 0 and minus 0.001. That is, this exactly satisfies the first equation and appears to come very close to satisfying the second one. Now, this on the surface, this might suggest the computed solution is very close to the exact solution, but we saw that it wasn't when we looked before. That's nowhere close to being close to the exact solution, which we found to be x equal 1 and y equal minus 1. Now, this is often a shock to students seeing this for the first time, and it's counter to a novice's intuition. Unfortunately, many students leave school believe they can always check the accuracy of the computations by simply substituting back in the original equation. It's good to know that you are not among those students. But this raises the question, how can I check a computed solution for accuracy? Well, fortunately, if the system is well conditioned, the residuals do provide an effective measure of accuracy. And well, we may, time permitting, talk about a proof of this later. I'm actually a little skeptical. We'll get to there. But this means that you must be able to answer some additional questions. For example, how can one tell beforehand if a given system is ill-conditioned? And how can you measure the extent of the ill-conditioning a system? And we will talk about this a little bit when we talk about the condition number later, but that's a long way from now. Now, one technique is to determine the extent of ill conditioning might be to experiment by slightly perturbing selected coefficients and observing how the solution changes. If it doesn't change, then you may say you're not sure, but you may think perhaps it is well conditioned. Here is the final LSA. I advanced the slide and can't go back. So we want to determine the exact solution for the following systems. And then I ask you to change 15 here to 14, and again solve it with exact arithmetic. Is the system ill-conditioned? And discuss your answer. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. God bless you all, and I look forward to seeing you in class soon.